Okay, great. So welcome everyone. Thank you all for coming. So today I'm going to talk about the work I've done in my graduate PhD in Brian Clark's group. I've been doing computational condensed matter physics. So today in the talk, I'm going to break up the talk into two parts. The first part will be about these inverse methods that I've developed. I'm going to talk about three projects very briefly, and then in part two, I'm going to talk about a more recent project on many-body localization. So in the first part, these three projects, since I discussed them before in the prelim talk I gave with my committee, I'm just going to give brief summaries of them. So I won't go into too much detail, but I'll go over a project where I developed a method for finding Hamiltonians with certain eigenstates. The second project, go over a method we developed for finding Hamiltonians to certain symmetries. And third project, we found a class of Hamiltonians to certain magnetic properties and these things called quantum many-body scars. And in the second project that I'm going to talk about, the second part, I'm going to introduce what many-body localization is and discuss about these conserved quantities called L-bits, and introduce an algorithm we found for finding L-bits, and then how we use that algorithm to find transitions for MBL physics in 2D and 3D systems. Okay, so first, let me talk about the inverse methods. So first, what do I mean by an inverse method? So kind of the traditional way people study quantum systems is using what I call forward method. So they normally start with some model of a quantum system they're trying to study. So that model is usually a Hamiltonian, and they solve that model to find properties of the quantum system they're interested in. So they're looking, for example, for the ground state or the excited states of their quantum system, or they could look for some symmetries. And this is kind of the standard approach people take to try to understand quantum systems. But I was interested in my graduate work in doing something a little different. I was interested in seeing if you could do the opposite problem, the inverse problem, where you start with some properties and you try to find Hamiltonians or models that exhibit those properties. So for example, can you find Hamiltonian with a certain eigenstate or certain symmetries? And note that this doesn't have to be unique. You can find many Hamiltonians with the same eigenstate. So that's why I'm drawing multiple arrows here. And so during my graduate work, I developed two methods for solving these problems. And that's basically what I'm going to talk about in this first part of the talk. Okay. But first, I want to give a little bit of background on thinking about Hamiltonians as vectors in a vector space. So we're used to, in quantum mechanics, thinking about quantum states as being vectors in a big vector space, a Hilbert space. But you can think of the operators that act on the quantum states as also being vectors in a vector space of operators. So for example, if you have n spins, quantum spins, you can write down a Hermitian operator that acts on those n spins using a basis of polystrings. So what that means is you can write the operator as a linear combination of these polystring operators, where these polystrings are products of Pauli matrices. So for example, sigma x, sigma y, sigma z, or identity. And since there's like 4 options for every spin, there's 4 to the n different possible polystrings. So there's exponentially many of them. And a general Hermitian operator can be written as just some linear combination of them with coefficients JA. So that's what I'm indicating here with this big red box. It's just a giant vector space of operators and represents all possible Hamiltonians. But what we're normally interested in physical systems is not just a complicated Hermitian operator, but we're interested in local operators. So we're interested in local Hamiltonians because in real physical systems, interactions are local. So in this case, what we're interested in are Hamiltonians that are linear combinations of k local polystrings. So polystrings that are made up of only a product of k Pauli matrices where k is just some small constant. So if you look at the dimensionality of this space, it's polynomial instead of exponential. And so the goal of these inverse methods is to find local Hamiltonians with certain properties. So with either certain eigenstate or with certain symmetry. which means this operator O commutes with the Hamiltonian. And it turns out these are also vector spaces. So we're looking for like subspaces of local Hamiltonians that have certain properties. Okay. So now let me go into the first project on finding Hamiltonians of certain eigenstates. So here's a schematic of the method called the eigenstate to Hamiltonian construction. So it takes as input a state and a space of local Hamiltonians, which you provide as input by specifying some basis of operators for this space. And then as output, you find the space of Hamiltonians with a certain eigenstate, with that state psi t as an eigenstate. And so the way this is done is by minimizing this objective function, which is the variance of your, the energy variance of your state with respect to the state psi t. And so the idea here is that for an energy eigenstate, the energy variance should be exactly 0. So if you can make this quantity 0, then you found Hamiltonians with your state as an eigenstate. And this quantity can be written as a quadratic form involving this matrix CT. Now this matrix is kind of the key quantity in this method. We call it the quantum covariance matrix, but it's basically a generalization of a statistical covariance matrix where instead of statistical expectation values with respect to random numbers, you take quantum expectation values with respect to observables. And this matrix has a number of properties, such as its Hermitian, positive semi-definite, which means its eigenvalues are non-negative. The eigenvectors of this matrix are vectors of coupling constants. So there are these JAs here. And so what that means is you can interpret the eigenvectors of this matrix as being a Hamiltonian. And now the eigenvalues corresponding to these eigenvectors are variances. So they tell you how much your Hamiltonian, like the energy variance of that Hamiltonian with respect to your state. So what that means is if you find any eigenvalues that are 0, you found Hamiltonians with your state as an eigenstate. And so I also want to point out that there's a number of papers that are released similar time as this work, where they also developed this, basically this method. Okay, but
good question.
Mm-hmm.
Basic one. I probably asked you this in the prelim too. So when you say Hamiltonians with psi as an eigenstate, doesn't necessarily mean that it's a ground state or an excited state or what?
Right. It doesn't mean anything about where it is in the spectrum. It can be a ground state or an excited state. Mm-hmm. Yeah. So this objective function is only guaranteeing you're going to be an eigenstate.
And if you know that the input psi is a ground state, can you guarantee that the Hamiltonians that you find also have that as a ground state, or can it be an excited state too?
It can be an excited state, depending on the situation.
Mm-hmm.
Yeah, I guess it depends on the space of Hamiltonians you provide as input. So if you knew your state psi t came from a ground state of some Hamiltonian, and this like space of Hamiltonians you provide as input included that Hamiltonian, you would find it. Right. But it could include other Hamiltonians where the state's not a ground state, but is an excited state.
Got it. Thank you.
Mm-hmm. Okay. So basically the method is essentially 2 steps. You compute the quantum covariance matrix for some state and some basis of operators, and then you diagonalize it and you look at its spectrum. And if you find any 0 eigenvalues, basically you found solutions to your problem. You found Hamiltonians with your state as an eigenstate, and any linear combination of these Hamiltonians will have your state as an eigenstate. But as we just mentioned, it can be anywhere in the spectrum. It doesn't have to be a ground state. Okay, and I just want to point out that this method is very flexible. There's lots of ways you could compute the quantum covariance matrix. So for example, you could use exact diagonalization. You could represent your state psi t as just a vector. It would be an exponentially large vector, but you could use it to do, using matrix vector multiplication, you could compute the entries of the quantum covariance matrix. You could also use methods such as tensor networks, where you represent your state psi t as a contraction of tensors. This is a class of quantum states that people have done lots of work with, and there's lots of techniques for computing various quantities like these. You could use techniques like variational Monte Carlo, which involves using Markov chain Monte Carlo to sample certain wave functions, so you can compute observables this way. Or you can even use experiment to measure the quantum covariance matrix. So you could use, for example, a quantum simulator or quantum computer to implement a certain quantum state in hardware, and then measure it using the tools you have in experiment to compute certain observables. So this method is pretty adaptable. You could use it in lots of different settings to try to find new Hamiltonians at certain eigenstates, or to like reconstruct Hamiltonians with states that you wanted to generate. Okay.
Well,
So now,
a simple question. Sorry to ask naive questions before we go on to the next topic, but maybe you'll answer the next topic. So in all of this, the Hamiltonians are Hermitian. Has any work been done, like you thought about, and again, I've probably asked you this before, has any work been done on non-Hermitian Hamiltonians, but say PT-symmetric ones that describe open quantum systems?
So as far as I know, no work has been done on that. I do believe you did ask this before, but I don't know about any work.
Yeah, okay.
Okay. So now I wanted to briefly talk about the next thing, which is a very similar method. And so this work was done in collaboration with a former student in our group, Benjamin Valanga-Correa, who's now at Google. And this method is very similar to the first one I introduced. This one's called the symmetric Hamiltonian construction. So now the main difference is now, instead of providing a state as input, you provide an operator as input. And your goal is to find operators, to find Hamiltonians that commute with this operator. So if it commutes with this operator, that means it's a symmetry of the system. So now the goal is a little different. Instead of minimizing the energy variance, you're trying to minimize the commutator norm. So you want this commutator H with O to be 0. So just you want to minimize the norm so it's 0. And again, basically same thing happens. It can be written as a quadratic form involving a matrix. And now this matrix is called the commutant matrix. It involves some commutators and traces, but it's basically a generalization of the quantum covariance matrix I introduced before. And again, it has the same properties. It's Hermitian, positive semi-definite. The eigenvectors you can think of as Hamiltonians, and the eigenvalues are now commutator norms instead of variances. And so again, you can just compute this matrix, diagonalize it, and see if you find any eigenvalues that are 0. In that case, those eigenvectors correspond to Hamiltonians with this operator O as a symmetry. And one thing that's a little different is you can compute the commutant matrix algebraically. So by that, I mean you can represent O as like a linear combination of some operators, such as polystrings. And then you can use the algebraic properties of polystrings to compute all these commutators and traces kind of exactly. So we wrote some code to do this. It's available here. Okay. But so one interesting thing that we did with these this symmetric Hamiltonian construction method is we found Hamiltonians with certain topological properties. So let me give a brief overview of how that worked. So topological order is a type of quantum order that exists in 0 temperature phases of matter. So it has a number of signatures. So topologically ordered systems have a ground state degeneracy that depends on the topology of the lattice. So for example, if it's just a plane or it's wrapped into a torus or something else, the ground state degeneracy changes. The number of degenerate ground states is different. Topologically ordered systems have what are called anyons. So anyons are like generalizations of bosons and fermions. So topologically ordered systems have exotic quasi-particles, and they have non-trivial long-range entanglement. So some examples of topologically ordered systems are quantum spin liquids and topological superconductors. So basically using this method, we were able to find new examples of these kinds of topologically ordered systems. So we could provide as input certain kinds of symmetry operators. So for example, these things called Wilson loops, which are these non-local symmetry operators, we provided as input to our method, and we were able to find new types of quantum spin liquid Hamiltonians that we could like numerically check behave like quantum spin liquids. And we did something similar with topological superconductors. Topological superconductors have these symmetries called Majorana zero modes. And so we could provide as input Majorana zero modes into our method and find new examples of Hamiltonians that commute with these Majorana zero modes. Okay, so that's a brief summary of what we did with this method. Okay, so now I'll get into the third project, which is about constructing Hamiltonians with certain magnetic properties. So in this project, what we did was we found Hamiltonians that could be built out of these motifs. So these Hamiltonians were a linear combination of motif Hamiltonians, and these Hamiltonians had certain what I call spiral colored states as ground states. These are certain kind of product state where the spin, each spin is pointing in the XY plane in a certain direction. So here on the right, I'm showing like a example of what this looks like. Here is a motif made out of 6 spins shaped into a hexagon. And this is what the spiral colored state looks like on the hexagon. And this is what the Hamiltonian looks like on this hexagon motif. It's got nearest and next nearest neighbor interactions. And so using these Hamiltonians, you can kind of just paste them together. And then by construction, the Hamiltonian you create on the larger system has these spiral colored states as ground states. So these motifs don't have to be built out of 6 spins. They can be built out of different numbers of spins. So here's examples like a motif made of 2 spins, 3 spins, 4 spins, etc. And just by like pasting them together, you can make larger lattices. And because of the way these Hamiltonians are constructed, you know exactly what the ground state is by construction. It's these spiral colored states that are drawn here. So here, for example, on the right is Penrose tiling. So it's like a quasi-crystal. And kind of, you know exactly what the Hamiltonian is, and you know exactly what the ground state is. So it's kind of an example of something you can construct using these motif Hamiltonians. And with slight modifications, you can create Hamiltonians with these things called quantum many-body scars. Let me briefly explain what that means. So quantum many-body scars are these high energy excited states with anomalous properties. So normally, high energy excited state of a quantum system has very high entanglement entropy, volume law entanglement entropy. But these scar states are very highly excited eigenstates that have very low entanglement entropy. So turns out you can use these motif Hamiltonians. If you add them up in the right way, you can create these scar states. So we did that in an example. We took a chain of pentagons, added them together in the right way, and then we looked numerically at the eigenstates of this Hamiltonian. And if you look, the eigenstates normally have very high entanglement entropy, but then these states down here in black are the scar states that have very low entanglement entropy. So they're kind of anomalous states. So it's pretty interesting using these motif Hamiltonians. You can construct Hamiltonians with exact magnetically ordered ground states where these scar states. Okay, and so now I should probably stop for a minute, take questions if anyone has any questions, because I'm going to move on to the next part. It's going to be about many-body localization.
Yeah, Eli, so maybe one question on sort of your recent PRR on the symmetry inverse Hamiltonian method. Mm-hmm. So for the new Hamiltonians you found, did you either target or did you find that they were better by some metric, either like maybe more physical to implement with some system or had some nicer properties in terms of gaps? Or were they just slightly different Hamiltonians that gave the same physics?
Yeah, so I guess for the spin liquid stuff, these Hamiltonians look very similar to the toric code on the Kagami lattice. So in this case, I'm looking at the Kagami lattice, and is basically like the toric code, but with extra terms. And because of these extra terms, it has different properties. So like the toric code is a sum of commuting operators. which makes it exactly solvable, but these are not sums of commuting operators. So it's a little different, but I agree these probably aren't very easy to implement in an experiment. But the bottom Hamiltonians, basically what we were able to do is we were able to construct like superconducting Hamiltonians. So that these are just like BDG Hamiltonians, non-interacting Hamiltonians with arbitrary Majorana-Zir modes. So you could kind of design whatever Majorana-Zir mode you want. Like it can be shaped, it can be distributed in space however you want. And you could find a corresponding superconducting Hamiltonian that realizes this Majorana-Zir mode. So I think there is a lot of potential in these Hamiltonians for experimental realization, but I guess it has to be in a superconducting system because you need the superconducting order in order to generate Majorana-Zir modes.
So I guess with respect to that, the first part with the spin liquid Hamiltonians, does this method, I guess in cases where there are exactly soluble results, does it let you kind of see how robust they are to deformations? Like I guess things are known about like the the SYK model and things like that. But if you see, in that case, it wouldn't be a Hamiltonian, or it wouldn't be an eigenstate. I don't know what you would search for that kind of Hamiltonian, but whether those sort of that phenomenology exists in more general classes of Hamiltonians.
Yeah, I definitely think you could use these sorts of techniques, either the eigenstate one or the symmetry one, to like study how things change with perturbation. So like, yeah, basically you could take something like a model with, I guess it's actually what you're thinking of is kind of like the Ford method. So you could take a Hamiltonian and try to find symmetries. So you could take like a Hamiltonian with a certain symmetry and perturb it and see how the symmetry changes.
Yeah, in your backwards case, I guess the finding these solutions in reverse sort of proves that the properties that you're looking for are robust outside of this exactly soluble limit of those cases.
Mm-hmm.
Okay. Maybe can I ask one more question about the scars? So the states you were showing, would one see like scar dynamics there? I guess one thing that's been seen in experiments, right, is that you see sort of long-lived dynamics without ergodicity or thermalization in these systems. Okay, so there are slight differences in those energies that you were showing.
Yeah, so sorry, I took this out because I thought maybe this is getting too much into the details, but yeah, there are you can see dynamic signatures of these scars. So here's an example of this. Like, so here I'm showing on the top like what the scar state or the spiral colored state. So these spins are in a certain state called C, and if you initialize in this state under this Hamiltonian, you time evolve, what you get are these like periodic oscillations. But if you start in some random product state, what you get is a very quick decay to the thermal value, which is zero expectation value. So basically, if you can in an experiment produce this kind of state as your initial state, you can see persistent oscillations. But if you prepare some different initial product state, you see a quick decay to thermal behavior.
Okay, thanks.
I had a quick question about the scars as well. Maybe it's a stupid question, but can you go back one slide, please?
Okay. This one?
So, yeah, exactly. So you didn't say anything about boundaries or boundary conditions. Are the scar states associated with localized states of the boundaries or something like this? Or what is their physical interpretation?
So no, these scar states, I didn't actually exactly explain what they are. So they are these spiral colored states, but projected into an SC sector. So basically there's this product state that I'm showing right here, for example, like the spins are aligned in this particular way.
Yeah.
And then you project into a certain like total spin quantum number sector. So it's some weird projected product state, which I don't know if it's very easy to interpret it as being associated with a boundary. I don't think it's associated with a boundary.
hard to know with a chain Hamiltonian. But I guess the other states are not obviously are on the same Hamiltonian. They don't have this property.
Right, and we just chose a chain because it's easy to do numerics on it, but these scar states should exist in all different lattices.
In arbitrary dimensions.
Yeah.
So when you say that they have subvolume law entanglement, how actually does it scale?
So we didn't work this out, but people in this paper, they studied similar types of states. And so these projected product states have logarithmic in system size entanglement entropy. So yeah, they don't scale like the system size.
Yeah.
Okay. Should I go on to the next part then?
Unless Jim or anybody else has any other questions.
Go ahead.
Okay, great. So now I'm going to talk about this project we did on many-body localization in 2 and 3 dimensions, again, done in collaboration with Benjamin. And so first, in order to understand what many-body localization is, we need to first explain what thermalization is. So thermalization is actually something we're all very familiar with in the classical world. So anytime you prepare a cup of coffee, you're experiencing thermalization. So what I mean by that is when you prepare a cup of coffee, you're preparing a very out of equilibrium initial state. It's very hot. And the surrounding environment, like the air in the room, is at a different temperature than your coffee cup. And your coffee cup can interact with the air in the room, exchange energy. And then over time, what happens is eventually it reaches thermal equilibrium. It thermalizes. And so once this happens, you can use kind of the statistical physics to derive various properties of how the system behaves. And you can, for example, determine the probability of being in a certain state. So the probability of the coffee cup being in a certain state is given by this Boltzmann distribution, e to the minus the energy of the state divided by the temperature. And so how does a quantum system thermalize? So in many ways, it's actually pretty similar. So you can imagine you have an isolated quantum system in a box. And so for example, let's say we're talking about interacting quantum spins. You have some quantum spins, they're interacting with one another. And let's say we want to focus on some subset of the spins in subsystem A. So these spins, because they're interacting with all the other spins, they're able to exchange energy with the spins in subsystem B. And so if you start in some like initially unentangled state, and then you time evolve, what ends up happening is all the spins entangle with one another. And so the spins in subsystem A are entangled with all the spins in the system, the spins in subsystem B. But if for instance, you're interested in what's going on just in subsystem A, you would need to compute the state on A, which, because the system's entangled with B, is a mixed state. So you can compute this mixed state using a reduced density matrix, and ends up looking like this, basically like a Boltzmann distribution, where you have e to the minus Hamiltonian on subsystem A divided by temperature. Now, how does this happen? How does a quantum system thermalize? So people understand this thermalization through this eigenstate thermalization hypothesis, which states that energy eigenstates of the Hamiltonian with finite energy density look thermal, or also called ergodic. So what that means is if you have an energy eigenstate psi n, and you compute its reduced density matrix on subsystem A, it'll look like this Boltzmann distribution. And so basically what this means is all eigenstates look like with similar energies look the same locally. They look like this thermal density matrix. And so a consequence of this is that if no matter what initial state you started with, if you time evolve for long enough, eventually there's like no local memory of your initial state. Your state will just locally look thermal. And so what that means is if you just look at subsystem A, you can't recover the initial state you started at. at early times. You'd have to look at the whole system A and B to recover your initial state. So information locally is lost. So this is kind of what happens in quantum thermalization. But do systems always thermalize? And so the answer turns out to be no. There are systems that fail to thermalize, and that's what I'm going to talk about. These are called many-body localized systems. And so the standard model of many-body localization that's been extensively studied is this model. It's called the disordered Heisenberg model. It's a spin model with XX plus YY plus ZZ interactions, nearest neighbor interactions between spins, and a random magnetic field on each spin. So these are random numbers between, these are uniform random numbers between minus W and W. W is called the disorder strength, and so increasing W increases the amount of disorder in the system. So it's the disorder that causes the system to localize and fail to thermalize. And so this is an interacting Hamiltonian. So interacting Hamiltonians are very hard to solve analytically or numerically. So you're kind of restricted to doing numerics on small system sizes. So this model has mostly been studied in one dimension. So for example, in this paper, they mapped out the phase diagram of this model. So on the x-axis is the disorder strength, W, and the y-axis is the energy of the eigenstates scaled between 0 and 1. So 0 is like the ground state, 1 is the highest excited state, 1/2 is like in the middle of the spectrum. And so they used various quantities to measure like whether an eigenstate looked thermal, whether it looked ergodic, or whether it looked many-body localized. And so they colored this plot accordingly. So here on the left, at low disorder strength, basically you find that all the eigenstates of the model, all the energy eigenstates look ergodic, they look thermal. But at very high disorder strength, all the eigenstates fail to look ergodic, they look many-body localized. And so there's some transition that happens around a disorder strength of 3.5 between these two regimes. That's where people have seen the many-body localization transition in one dimension. Kind of a big open question is, does MBL exist in higher dimensions? So because of the difficulty of studying MBL numerically, this is still not very well understood.
I'll ask a naive question before you get into the details. So I just wanted to understand, you know, when we talk about thermalization as being equivalent to losing the local memory of the initial state. So is it obvious what that really means, you know, losing the local memory of the initial state? Because there's different ways that one can lose memory. For example, let me again, this may be a question I asked you in your prelim, but you know, if we think about, say, dynamical systems, one typically thinks that one loses memory of the initial state in time exponentially. But in some systems, again, not, you know, nonlinear PDEs and things like this, you find that the system at long times will still remember in a weak way the initial state. The best example of that would be scale interference in critical phenomena, where you have at long wavelengths, you know, scaling laws and say the correlation functions, but they, you know, what people sometimes say is that they violate dimensional analysis. But what's actually happening is that the scaling law is has some memory of the, you know, the lattice size or the ultraviolet cutoff, and so the existence of that allows that means that it comes into the correlation function. It alters the critical exponent, but the critical exponents still are universal in the sense that they don't depend on what that scale is, and that comes about because you've got the sort of power law decay of the correlations in space, but you could have similar things in time as well. So have you or have other people thought about that nuance, about what one really means when one says losing memory of initial conditions?
I guess I don't quite know exactly how to answer that. I haven't thought about it too much personally, but I'm sure probably people have. I think there's like precise senses in which people mean like how the memory is lost. Like if you start with a certain initial state where the state is a linear combination of energy eigenstates that are like in some narrow band of energies, then you can't recover what the initial state was if the eigenstate thermalization hypothesis is satisfied. But if your state is like a linear combination of eigenstates with very different energies, I think there is some memory of the initial conditions. So I think it depends on how you initialize your state precisely.
Right, because I mean, yeah. Because I mean, you do get a similar thing in critical phenomena, and you always say, well, a system should lose memory of its small scale structure, its ultraviolet structure, but that breaks down at a critical point in a particular way. It doesn't mean that you still can't have a thermal system. It just means that you have a slightly different scaling for the correlations, and there's ways to detect that in critical behavior. Well, okay, and I don't want to randomize it, but okay, but you haven't seen anybody sort of make that particular connection in this context.
I can't think of anything at the moment, but I do think it's interesting when you're mentioning how this like local memory of initial conditions changes near the transition. I definitely think that could be interesting to think about. I feel like there must be some local memory, like as you approach it from the MBL side, you should still remember the initial conditions somewhat. So in the transition region, probably some memory.
Yeah, exactly. And even in not in quantum systems, even in just PDEs, but non-equilibrium dynamical systems, there's many examples, huge numbers of examples that people have studied where in fact we developed RG ways to detect how these systems they kind of lost the memory of the initial conditions, but not completely, and you could see a sort of relic of the some quantity characterizing, say, the size of the compact support of the initial condition or something like that, even at arbitrary late times, even though the system was exhibiting fully scale invariant behavior. And so you'd think that you would not be able to detect something about the initial conditions. So, okay, well, anyway, the way you explained it was very good, and it triggered me to think of this question.
Okay. Great. Maybe it'll make a little more sense as I explain more.
Well, no, everything you said makes perfect sense. It just made me think about, well, there could be a more nuanced way of thinking about this.
Right. Okay. Well, I think as the discussion will continue, it'll maybe answer some of what you're thinking about.
Yeah.
Okay. So I just wanted to say that many body localization is still an active area of research. It's still not completely understood exactly how everything works. And so one thing that there's not like a complete theory, but there's a lot of properties that people have determined about many body localization, about how MBL systems behave compared to ergodic systems that thermalize. So here I'm just listing a bunch of these properties. I'm not going to go into detail on all of them, but I'll mention a few of them. So as I mentioned, ergodic systems satisfy this eigenstate thermalization hypothesis, but MBL systems don't. But also I want to focus on kind of these last 3 points that I'm going to explain a little bit more. So as we already talked about, ergodic systems have no local memory of initial conditions, but MBL systems do. Ergodic systems also, the entanglement entropy, if you start from an unentangled state, grows linearly in time. But in MBL systems, it grows logarithmically in time, so it's much slower. And a key thing is in ergodic systems, there's no local conserved quantities. There's only like global conserved quantities like the energy.
So quick question. So there's no systems that have a power law growth of the entanglement in time after a quench?
So actually, I think there are. I think normally it's linear, but I think it can be polynomial in time.
Well, what's different about those systems that have a power law?
So I'm actually not sure. I believe I've seen it, but I forget what context it was.
Mm-hmm. Cool. Thanks.
Yeah,
So I think
sorry.
it's long range interacting systems sometimes have power law growth. And so if you have long range interactions, I think that can induce that.
Right. Yeah, that makes sense. Yeah.
Okay, thanks, Brian. Okay, and so
But
in
then you could also, Brian, you could also have that even if you had short range interactions. I mean, there's the range of interactions, and then there's the range of correlations, and those things are different. And so, did anybody see power law growth in Quench as you go close to the ergodic MBL transition?
I don't think anyone on the MBL side has seen that. There's some confusion on the ergodic side heading to the MBL side because there's some subdiffusive behavior there.
Right.
So things are a little bit subtle on that side. And so that one would have to think about a little bit more carefully. But as far as I know, the long range interactions is the only thing that gives you sort of the super linear growth, at least what I remember off the top of my head.
Right. Yeah. I mean, that's sort of dialing it in by hand, as it were. But it'd be interesting.
In some sense, because you're making it sort of.
Yeah.
You're not local.
Yeah.
Yeah.
Okay. Cool. Thanks.
okay, and so right, so I was just saying that ergodic systems have no local conserved quantities, but in MBL, what happens is there are these emergent local conserved quantities called local bits or L bits, and so these L bits are kind of key part of the story of MBL. If they exist, they imply a lot of the other properties of MBL systems. Okay, so let me talk about what these L bits are. So first, for a general Hamiltonian, you can find a unitary U that diagonalizes it. And from that, you can construct these operators tau iz, which are U, sigma iz, U dagger. And from these tau iz operators, you can kind of re-express the Hamiltonian in this form, where it's a sum of these tau iz's plus sums of products of these tau iz's. And so this is basically just the form of a diagonal Hamiltonian, just written in a certain basis. And these tau iz operators have a bunch of properties. They're conserved quantities. They all commute the Hamiltonian. They mutually commute with one another. They're traceless, and they're binary. So their eigenvalues are plus or minus 1. And so in general, for a general Hamiltonian, these tau iz operators are very complicated. They're very like non-local in space. So it's hard to work with them and think about them. But in MBL Hamiltonians, these operators are pretty simple. They're quasi-local, which means they're local up to exponentially small corrections. So for example, you can think of a tau iz operator as basically just a sigma iz operator plus some dressing. And so because of that, these things are called local bits or L bits, and they're a key signature of MBL physics. So for example, here's a cartoon showing what an L bit looks like. So this orange blob here is supposed to represent an L bit at site 4. So it's basically localized spin at site 4, but it exponentially kind of goes into the nearby sites. Okay, and so these L bits kind of describe a lot of the properties of MBL. So that's what I'm going to talk about here. These L bits, if you suppose that they exist, you can deduce other properties that MBL systems have. So for example, L bits lead to like a local memory of initial conditions. So because this L bit commutes with the Hamiltonian, you can just in one line of algebra show that the expectation value of this L bit over time doesn't change. So for example, if you start in some initial state at time t equals 0, and you measured, let's say, the 4th L bit, and you got some expectation value, let's say it's 0.3. You then time evolve for arbitrary amount of time, and then you again measure this local observable, you should get the same exact value. So just by looking locally, because these L bits are local operators, you can determine what the initial condition of your system was. So clearly there is some local memory, and L bits imply this local memory, which implies that the system doesn't thermalize.
You can measure them experimentally.
Maybe at high disorder strength you could, because the L bits are very high disorder strength. They're very, very local.
Right.
But once you get to low enough disorder strength, these L bits are complicated enough that I think it would be quite hard to measure them. But also kind of maybe the more, I don't know exactly how you would know what the Albits are unless you knew exactly what the Hamiltonian was. So like if you were doing an experiment where you could exactly control what the Hamiltonian was, so you could exactly determine what the Albits were like before you did the experiment, then you can measure the Albits. But if you didn't know what they were beforehand, I don't know how you'd measure them. Does that make sense?
Yeah.
Okay.
So could you do them in a quantum simulator? You know,
Yeah.
you're doing like a sort of cold atom type experiment where you can control things.
I think in principle you could, but I don't know what exactly how hard it is to measure certain quantities in a quantum simulator. It might be like infeasibly hard to measure, but
Yeah.
I wouldn't know. There is a cold atom experiment I'm going to mention in the next slide actually. They don't measure Albits, but I'm just going to explain that they do study MBL with a cold atom simulator.
Okay, thank you.
So another thing the Albits implies this logarithmic growth of entanglement entropy. So very roughly, I can explain how this works. So if you have an MBL Hamiltonian, as I mentioned in the last slide, you can write it like this in terms of the Albits, where because the Albits are quasi-local, these Jij's decay exponentially with distance. And so what can happen is if you initially had some state where the spins I and j are unentangled, roughly you need to wait a time 1 over Jij, this 1 over the coupling between the spins, for the spins to become maximally entangled. Is that can tell you like the radius in which spins are maximally entangled is given by this. It grows logarithmically in time if you just combine these two equations. So this roughly tells you that entanglement entropy should grow logarithmically in time. So this is a sense in which Albits can lead to logarithmic growth of entanglement entropy. Okay, but now I'm going to talk about MBL in 2 and 3 dimensions. So I wanted to explain an experiment that was done to study a 2D system. So this is an experiment from this paper where they did a cold atom quantum simulation of the 2D Bose-Hubbard model. So they had bosons in an optical lattice, rubidium atoms, and so they subject them to this interacting Hamiltonian, which includes a disordered chemical potential term. So there's like random chemical potential. And they basically varied the amount of disorder and initialized the quantum simulator into some state where the atoms are initially out of equilibrium and then watched how the system time evolves. So in particular, they looked at, they initialized all their atoms in the trap, and then they somehow kicked out half the atoms so that the atoms are only left in the left side of the trap. And then they time evolved. So on this left panel, I'm showing the case without any disorder. And so this should be the ergodic regime where it thermalizes. And so what you see is if you time evolve, eventually the atoms at late times spread out throughout the whole trap, and they're spread uniformly, basically, or evenly. And then they also did the same experiment at different disorder strengths. So this is an example where they did a high disorder. And what happens is even at very late times, there's this imbalance between the number of atoms on the left and on the right side of the trap. And so they could quantify this imbalance and measure it over time. And they see like for the low disorder experiments, they very quickly decayed to 0. But for the high disorder experiments, at long times, it stayed non-zero. And so if you look at the late time imbalance versus disorder strength, what you see is that for disorder strengths below some value around 5.5, the system always seemed to equilibrate. So they thought this is the ergodic regime. And above this disorder strength, the system imbalance is non-zero at late times. And they said this is the MBL regime. So they claim to observe a transition between ergodic and MBL behavior in this 2D interacting system. So this is a very interesting experiment, and people are trying to understand it. So there have been various studies trying to see if they can find agreement with the experiment through numerics.
So is the decay of the imbalance exponential to its asymptotic state?
It's a good question. I'm not sure.
I mean, it kind of looks like it might be, but did they figure that out in detail?
Yeah, I actually don't remember. I don't remember reading that. Yeah, sorry, I don't know. It does look exponential from this plot, as you're saying, but it's hard to say.
Right, because it kind of, the reason I ask is it kind of relates to my earlier questions, is can you get a system which is kind of intermediate, where it still decays at long times, the imbalance, so it looks like it's ergodic, but it decays with a power law rather than as an exponential. Kind of like when you look at off diagonal long range order in a 2D quantum system. It'll still eventually go to zero, but you'll have a power law decay rather than exponential decay, indicative of some intermediate phase.
Yeah, that's a good point. I guess to really know if that's the case, I guess you need to do a simulation for a really long time. But unfortunately, like to get many decades of time, so you could clearly see whether it's power law or exponential. But in these experiments, I know that they can't go too long because eventually, like this system isn't a perfectly isolated quantum system. These quantum simulators, like eventually, the system's open, so it eventually would thermalize if you waited long enough. So there's like some window of time in which you can think of the system as like being perfectly isolated, but beyond that, it will always thermalize.
You could do some kind of finite size scaling, right, where you artificially control the rate at which it thermalizes, and so then you see how that sort of cutoff time changes with the thermalization coupling, and so you could, it would be like doing finite size scaling in critical phenomenal field theory. So that might be a way to try to look to see if there's some kind of way of getting a power law. I don't doubt that this is probably exponential in this particular system, but I'm just wondering if one looks at other systems whether one can find these intermediate states where you would have this sort of power law approach to ergodicity as opposed to MBL, so something intermediate. Anyway.
Right. No, I definitely think this is definitely something that should be sorted out, especially with the MBL case. I mean, it seems like it decays pretty slowly here, but it's not obvious that it eventually plateaus. It could be eventually at very late times that it actually still goes to zero. So, yeah. So I think this.
I mean, this is something that would, if it happened, if what I'm saying it happens at all, it would happen at in low dimensions, and so it may not happen in 3D, but it could happen in 2 or 1D. Okay, cool, thanks.
Yep. Okay, so next I wanted to talk about a numerical study done of 2D MBL. So there was a study by in this work where they analyzed the same model that the experimentalists looked at, the 2D Bose-Hubbard model, using tensor networks. So I won't go into the details of this study, but basically they have an algorithm for finding L bits using some tensor networks. And from these L bits, they could obtain approximate energy eigenstates of the Hamiltonian. And so using this numerical method, they found they can measure various properties of for example, the eigenstates. They could look at the entanglement entropes and look at the variance of it. And they saw that it peaked at some disorder strength. And this, as well as other signatures that they measured, indicated that the transition happened around a disorder strength of 18 in this model for a particular type of Bose-Hubbard model and in the limit of hardcore Bose-Hubbard model, which means there can only be one boson on each lattice site. Okay, and they also measured various quantities like the correlation length of the L bits. And so I just wanted to mention this because this is something I'm going to compare against in my calculations. Okay, so now I'm going to talk about what we did. we developed an algorithm for finding L-bits, which could be used in arbitrary dimension. So the goal of our algorithm is to find L-bits and minimize this objective function. The objective function has two parts. The first part is the commutator norm, which measures how much the L-bit fails to be a conserved quantity. And then the second term is the binarity, which measures how much the L-bit fails to be binary. And what we do is we represent the L-bit using a small basis of local polystrings. So our L-bit is just a sum of these polystrings, and we have to determine these coefficients. So that's what we do in the optimization. Using a finite basis, we optimize these CA coefficients to minimize the subjective function. And so the steps of our algorithm are basically this. We initialize our basis initially with just one polystring, just sigma, a single polymatrix sigma iz. And the intuition here is that our L-bit, we expect it to be in the MBL regime to basically be sigma iz plus corrections. So this is kind of the most important term of the L-bit that we first add to our basis. So then what we do is we expand the basis by adding new polystrings in some smart way. And then we optimize the coefficients of our polystrings to minimize that objective function. We just use gradient descent to do that. And so then we just repeat steps 2 and 3. We keep expanding a basis and optimizing over and over again. And I didn't really explain the details of this step 2, but there's some heuristic we have for adding new polystrings to our basis that depends on what the current L-bit looks like. So the idea here is to try to smartly add polystrings that make sense to add.
How do you choose which polystrings you add?
Yeah, so that's what I'm trying to explain here.
I understand you have a heuristic to expand it, but how do you know? I didn't understand how you choose. You've got lots of choices that you can add. So how do you choose which ones?
Yeah, so we basically let the Hamiltonian tell us what to add. So if you compute the commutator of Hamiltonian and the current L-bit, you're going to get some operator out. And that operator is basically how much your L-bit fails to commute with the Hamiltonian. Like it's some leftover remainder term, right? And now the idea is you want to then cancel that remainder. And so what polystrings you want to add to cancel? Basically, to figure that out, you need to take another commutator, Hamiltonian. So that's why there are these two commutators. Like you take two commutators, and then you'll get some list of polystrings. And we choose basically the polystrings here that have the largest coefficient.
I see. Okay. Yeah. So like everything, I'm always just mapping this into field theory. So this is like making an improved action in field theory.
Okay.
Okay, yeah. I understand, thanks. That answers my question,
Great, yeah. It's interesting that, it's good to know that there are things that are similar to this, because I didn't know about an improved action thing. So maybe there's a smarter way to do this.
Probably you're doing it the smartest way, but it's just a way. I now have a label to attach to it in my brain, which I can understand what you're doing in my own language. Yeah.
Mm-hmm.
Okay, thanks. Yeah, that answers my question.
Okay. Right. So I was just going to say that our algorithm for doing this is available here on GitHub, and here's a schematic, kind of what's going on in the algorithm. So let's say we're trying to find an L-bit at site 5. Initially, our L-bit is just sigma z at site 5. And so our basis is this bucket with one polystring in it, sigma z at site 5. Then what we do is we use our smart basis expansion procedure to add polystrings to our bucket, and then we re-optimize our L-bit. So now instead of just being sigma z, it's like some optimized L-bits, 0.9 sigma z plus corrections. Now using this optimized L-bit, we again add new polystrings to our bucket. And now with a bigger bucket, we could re-optimize the L-bit over and over again. So this is the procedure. And at every single step, the L-bit should become more and more accurate. The commutator norm and binarity should both go down. Okay.
Eli, can I ask one general question? So in thinking about just the difference between like an ergodic regime and a MBL regime, I guess you expect your eigenstates to change quite a bit from things that have like purely local support to things that are delocalized across the system. What would one expect if you really had a system that had like glassy dynamics? Would there be things that look kind of like L-bits as well there that are hard to distinguish from L-bits, or?
Yeah, I guess I'm not super familiar with glassy systems. Like, how, could someone briefly give me an explanation of like what distinguishes the glassy system from just a disordered interacting system?
Well, I mean, in your last case where you were showing these results from Emmanuel Bloch's group, right? One would have to look over, like you said, many decades of timescale, and on the few, 100 tunneling times that you showed, there's basically no difference. I think that what they're claiming is MBL. One would have to kind of go out longer to see if there's relaxation on much longer timescales. I think that's what I would associate with the glassy system.
So you're saying it's like if it's like power law decay, you would associate that with glassy.
Maybe there's some metastable states and some really slow relaxation.
I see. Yeah, I think you would basically still get something like an L-bit, but probably the way the L-bit like decays in space is probably different. Like the scaling, I'm guessing, of like how localized it is probably different, or maybe how well it commutes at the Hamiltonian scales differently. If that makes sense.
Yeah, so in the same sense of the experiments of sort of having to get to some level of precision there, sort of in going to long times to distinguish the difference, would one have to do the same thing with sort of identifying L-bits to distinguish the difference between MBL and glassy physics?
I imagine probably you do need to do something like that to be really careful about it, to understand kind of the difference between this and like more traditional, like the MBL you get in 1D. So maybe it is different in how things scale, like how the L-bit decays with distance might be different than in 1D.
Okay.
I'll ask another question. In terms of the convergence shown in this sort of repeated construction, is the convergence uniform, or do you ever see non-uniform convergence, and does it always converge, or does it can you get a situation where actually it looks like it's getting smaller, the commutators, and then it starts to grow again?
So we've looked at this numerically. I don't think I had a slide on this, but empirically we saw that it always decreases the objective function at every single step of the algorithm. But it's not like it normally plateaus at like some like optimal value. It just always continuously decreases. It actually like slows down how quickly it decreases. So yeah, basically we just go out to some basis size that we can afford given our like numerical resources and just go up to that basis size. But you would in principle need to go bigger if you wanted to really get more and more accurate results.
Yeah. Okay, thanks.
Okay, so let me just briefly explain what models we looked at. So we looked at 4 different models. First is the disordered Heisenberg model I mentioned earlier, in 1 dimension, 2 dimensions, and 3 dimensions. So remember the 1D model I'd said had been studied a lot, but actually the 2D and 3D models hadn't been studied before numerically. And we also looked at the disordered hardcore Bose-Hubbard model, which is that same model that was studied in that tensor network paper. And actually this can be rewritten as a spin system. So, and we studied it in 2 dimensions. So we did this basically to compare with the tensor network study. Okay, so now let me talk about how good our L-bits were from our algorithm. So here are results for the 1D Heisenberg chain. We're showing on the y-axis the commutator norm and binarity, and on the x-axis the disorder strength. And so in red is the commutator norm, in purple is the binarity, solid lines the average, dotted lines median. And just to remind you, the transition happens in 1D model around disorder strength of 3.5. So what you expect is that left of that, the system should be ergodic and there shouldn't be any local conserved quantities. There shouldn't be any L bits. So the algorithm shouldn't be able to find anything. But in the high disorder strength limit, the system should be many-body localized, and the algorithm should be able to find L bits reasonably accurately. And that's basically what you see, that these numbers are much lower on the right side, and they get worse as you go left by orders of magnitude. And the median is normally a lot lower than the average, because the average is kind of dominated by outliers because you're doing random sampling. Okay. Yeah, and it's interesting, it goes kind of smoothly. So you can't really see the transition just by looking at the subjective function, which you might have expected to be able to see. Okay, and so here are the results for 2D and 3D. And so I just want to focus on the orange lines. So the orange lines are the results for the 2D Bose-Hubbard model. And I just want to point out that these orange open diamonds at the top are the results from that tensor network study on the same model. And so they were orders of magnitude higher than our commutator norms. So it gives us some confidence that our algorithm is doing decently well. Okay. Now let me talk about kind of some properties of these L bits. You can look at these L bits in space, look at their spatial distributions. And here I'm showing it for 1D, 2D, and 3D. And you can look at it versus different disorder strengths. So this blue one right here is the high disorder strength case, so the L bit's very localized, just at one site. But as you decrease the disorder, it becomes more and more non-local. But it doesn't really fully delocalize because we're using a small finite basis of polystrings. So we can't really express the full non-local operator in the low disorder strength limit. But yeah, and so basically we see the same behavior in 2D and 3D. And what you can do is you can fit these spatial distributions of the L bits to exponentials and extract a correlation length. And doing this, we get some estimate of the correlation length in the system versus disorder strength for the different models. And we get a decent agreement with previous studies of the one-dimensional Heisenberg model and the 2D Bose-Hubbard model. At least a high disorder, it agrees quite well. Yeah. Okay. And then maybe the most interesting thing we found is that by looking at the L bits, you could see a signature of a transition between the ergodic and the MBL regime. And so the way we saw this transition is by looking at this overlap, which measures how much the operator tau iz overlaps, how much support it has in sigma iz. So if this value is like close to 1, then the operator tau iz is almost sigma iz. And so what I'm showing here on the left is an interpolated histogram. On the x-axis is the disorder strength, and the y-axis is the overlap. And basically what you can see is that at high disorder strength, basically all of the L bits have very high overlap near 1 with sigma iz. And in the ergodic regime, they have very low overlap, very far from 1. So on the right here, I'm showing the same plot with like a cutoff applied, just to make it easier to look at. And so you can see, as I was saying, basically all the L bits here are, all the tau iz operators are basically sigma iz. The overlap is basically 1. And then abruptly at some disorder strength, what happens is there's some kind of abrupt change where suddenly all of the operators are non-local and are not just sigma iz plus corrections. And so we could see this empirically, and it seemed to align very well with the where the disorder, where the transition is expected to happen in the 1D Heisenberg model. So we take this as an indicator of an MBL transition. And so then we looked at this in all the different models we studied, and we saw basically the same sort of behavior. So here, for example, is the 2D Bose-Hubbard model, and you see this behavior where it steps down in the overlaps, and there's some region where this step happens, and from that we could estimate roughly where we expect the MBL transition to be. And it's a very large region. It's not super accurate, but it seems consistent with the tensor network study that I mentioned before. They measured it to be around disorder strength of 18. somewhere in here. But the interesting thing was that we were able to provide the first estimates of an MBL transition in the 2D and 3D Heisenberg models. So it's particularly interesting for the 3D case because as far as we know, this is the first numerical study of MBL in the 3D system. So we could provide an estimate of where the MBL transition happens in this case. And it'd be interesting to see if future numerical work or experimental studies would be able to detect the transition around this disorder strength.
What does it mean? Maybe I'm misinterpreting. What is it when you look at these sort of these plots on the right where you've done the cutoff? What does it mean? Is there any special meaning to this sort of what's the word? Any fixed value of delta that there's it's not single valued for the overlap. It's multi-valued. Does that mean anything, or is it just?
Yeah. So you're saying why are there two regions? Why are there like two?
Yeah.
So this is sometimes called bimodality. Like if you look at the histogram at a fixed disorder strength, you would see two peaks.
Yeah.
And so this kind of bimodality has been seen before in MBL when you look at various other quantities, like people have looked at like entanglement entropies, and you'd see like in the region where the MBL transition happens, like there's the eigenstates like fit into like two camps, one that has like high entanglement, one that has low entanglement, and they coexist in this like range of disorder strengths.
So does that mean that transition is a first order transition in some sense?
Right, yeah. So this is one thing that's still not very well understood, I think, but there's some indicators that the MBL transition looks first order because of this sorts of like bimodality.
Yeah.
But there are other indicators that it looks like a second order transition because like scaling arguments, like sometimes you can get like scaling collapse and things of various quantities. And so people don't really understand how those two can coexist, I think. It's still not well understood.
Yeah, I don't suppose anybody's looked at hysteresis.
I don't know. Maybe.
That's interesting. Okay, thanks.
Okay, and so actually that was basically all I wanted to say.
Eli, maybe following up on that, I guess for this bimodality in these systems, is the general picture that the system actually has sort of spatial segregation and sort of insulating and metallic puddles? I mean, that's true, I guess, for this 2D case, but I don't know if some similar thing applies to the spin system because it's disordered. That's sort of where the bimodality shows up.
Yeah.
Is that the picture you have in mind of where it stems from in this case?
I mean, I don't know if I have a very clear picture in my mind what's going on near the transition, but that seems to be a reasonable picture. Like a lot of the L bits are still quite localized, but some of them start being delocalized. So I wouldn't be surprised if there's like some fraction of L bits are like localized and around it are like puddles of like thermal system. So I think that's reasonable, but I don't have a very clear picture in my head.
Okay, thanks.
Okay, so I just wanted to provide a little outlook on this MBL study that the algorithm we developed is pretty general and can be used to study MBL in different geometries and potentially in geometries that you could access using like quantum simulation experiments. So it might be interesting future work to do. There is this heuristic basis expansion part of the algorithm I mentioned we talked about, and I'd be interested to know if there's other ways you could do this that are maybe better, so the algorithm converge faster. And there's certainly lots still to explore about LBITs and what we looked at. That'd be interesting to do. And so to summarize, in the first part, I talked about these inverse methods that we developed for finding Hamiltonians with certain properties. And the second part talked about this numerical study I did of many-body localization in 2 and 3 dimensions. And so I'd like to thank Brian for being a great mentor and for to everyone in my group for all the wonderful conversations we've had over the years. I'd like to thank especially Benjamin for the great collaborations we had. And I'd like to thank my friends and family for all the great times we've shared together in the last few years. And finally, thank you all for listening.
Okay, great. Thank you. So any other questions from the committee members?
I have a question. So can you also get localization due to irregularity in geometry? So you have been studying regular lattice structure, but can you also get localization due to, for example, studying on random graph?
That's definitely an interesting question. I don't know. So I showed here some examples of lattices, like these are frustrated lattices, like triangular Kagame. So definitely if you have lattices like this, you can get interesting physics like frustrated magnetism. So it would be interesting to study, for example, how disorder is affected by things like this, but also, yeah, what you mentioned is definitely interesting too. Like that's a different type of disorder you could study if you just randomly remove edges in a lattice, or you just have a random graph. I definitely would expect there to be some kind of localization physics there. But I guess maybe it's like a little less intuitive of how that connects to like a real material. But it would be interesting to study just in general.
Right, so it may not be applicable for material science, but right now, as you know, social network analysis or biological network analysis is really of interest to many people, including people like us in physics. So I had a student who studied network of biological systems where the edges are more or less randomly sampled due to interaction between genes, for example. And we studied quantum mechanics on these graphs, and we've also found localization phenomenon. And I was just wondering whether we can apply some of the techniques for understanding the structure of graphs that naturally arise in biological or social systems.
Right. No, it definitely sounds interesting. And I think this algorithm would be useful because this algorithm is kind of agnostic to what lattice you're using. So, or what graph you're using. So it's definitely possible to study such systems. I guess I don't quite know why, like I understand why you'd want to study these graphs in the context of biology, but I guess I don't know why you'd want to put an interacting quantum Hamiltonian on such a graph.
Yeah, so it's for clustering phenomenon. So people are interested in clustering nodes. So when you have graph Laplacian, for example, you can study the spectral property of the graph Laplacian, which is manifested in the clustering structure of the nodes. So we try to do something similar by looking at Hamiltonian version of what people have been doing. And we found that the wave functions could be used to characterize the clustering behavior, but the behavior of the propagation of the wave is quite localized. But what we found is that we can actually use the phase information of the wave function to cluster nodes. I was wondering about whether people have studied random graphs. For example, there's a phase percolation phenomenon in Erdős-Rényi graph as a parameter of the sampling of the edge probability. And I believe some physicists have looked at this kind of localization phenomenon on Erdős-Rényi graph. So I was wondering whether you have also looked at some kind of localization due to disorder in geometry.
So I haven't, but I agree that is interesting. I would be curious what that would do.
Does anybody else want to ask any questions, whether on the committee or on the guests? Okay, well, it seems not. So so I think at this point, Ellie, you can send the committee to the breakout